What's up, guys? Today we're going to be looking at macroscopic energy balances, and we did this for a pump. We looked at the macroscopic energy balance around a pump and found that the pump work would be something like the volumetric flow rate times the pressure drop, or the pressure increase that we expect between the suction eye and the discharge line of the pump. Today we're going to do something a little bit different. We're going to apply this to an ideal gas, and this ideal gas is going to be flowing through a nozzle. So what we have is a very large reservoir, and we have a converging nozzle. And so we'll have an environment out here where we have static conditions. So we might have like the environment temperature. We could have, actually let's call this O. T naught, P naught. The velocity out here equals 0. It's a quiescent environment. And then in the reservoir as well, so this is an infinitely large reservoir. We have, say, the temperature of the reservoir, a higher gauge pressure inside of the reservoir. And again, the velocity in here is going to be 0. We'll call those the average velocities. And we want to look at an ideal gas as it's flowing through here, through this nozzle. So we'll be looking at, say, the exit velocity. We will look at the enthalpy change for sure. We'll look at what we're going to call, and we'll realize the significance, the critical pressure and the critical velocity as we reach that critical pressure of this gas. Critical pressure and velocity. And ultimately, we're going to see how this relates to rocket science and look at the design of something we call it the Laval nozzle, and look at how we can actually get vehicles to exceed the speed of sound. And the speed of sound happens to be this critical velocity that we're going to figure out with this gas. So we'll need to define our control volume. And we'll take the control volume to be just the gas in the nozzle itself. We have 0 velocity outside of this control volume on both sides. But in the control volume, we have an acceleration of the gas and a big change in pressure. We'll consider this to be compressible for sure. There'll be a big difference between doing a liquid through a pump and a gas through a nozzle. And I think we're about ready to set this thing up. So let's set up a bigger control volume. This up a little bit. And actually, first of all, we have our control volume here. The energy balance we're going to use is basically a statement of the first law of thermodynamics. We could look at this as from state 1 to state 2, a delta of the mass flow rate times. So we kind of think about this as a open system. It is an open system, but all the energy that this fluid could possibly be coming into our control volume, we want to make sure we include. And whatever energy it leaves with, we want to make sure we subtract. So we'll have, it might come in at a certain specific enthalpy, right? The enthalpy of the fluid might be really high or really low as it's entering this control volume. It could have certain kinetic energy. And we might consider gravitational potential. I don't think we'll be doing that with a gas, right? We typically neglect gravity when we're talking about gases, and we'll do that in this case. But we could possibly have a gravitational potential, and possibly we could do work on the system, or we could have heat transfer, and we could do work on the system, right? This is a statement of the first law, and that could equal a change in this control volume, the energy in this control volume, with respect to time. So that's everything that we could have. And then for our system here, let's see what won't really be so relevant for us. We are going to consider an adiabatic system. So adiabatic. We are having a gas, so we're not really going to be concerned with the gravitational potential. We aren't going to do work on this system. So it looks like right away we can reduce this down to a change in enthalpy of the system associated with a velocity change in the system, right? We know that maybe V1 we considered to be 0 and we had an acceleration to V2. And this is set up for a change in energy in this control volume over time. And we have to consider, do we expect this to change over time, or can we consider this to be steady state? We can allow for a spatial change in energy and in enthalpy while still maintaining steadiness with respect to time. And that's what we'll consider. We'll consider this to be steady in time, but have a spatial enthalpy change. That's what we're trying to capture. So with those assumptions, we can rewrite this law as delta m dot, and we could distribute this, why not? All right, so we have our first law for an open system, also known as our macroscopic energy balance for this nozzle. And so we'll set up a little bit larger control volume and start figuring out what exactly this delta is.